Okay, actually before that, before we start class, right, just wanted to show you something. I think I finally got around to correcting the project once, and I'll be sending this by email to all of you guys. But this just shows the distribution of the queues. Okay, that's the main objective of project 1, right? So, like whatever, 30 students, you have distribution from all the way from 5.1 all the way till around 8.2 or 8.3. Okay, and to show you, what all each people have done. So the ones 7.7 to 8 are all using octagons, which is, we discussed that, right? Octagons are much better, they have a much better area efficiency. They're using multi-layers because in our case we decided to turn off the AD parameter, right? So your AD losses are much lower. So what that means is you can go down to a lower metal layer and still end up getting a decent Q. Okay, it improves the Q, but doesn't degrade the AD losses doesn't degrade the Q that much. Okay, and then there was one person who used a tapered square plus a multi-layer. Okay, so you all must have seen what the tapered square looks like, right? So most of the inner layers are made thinner. So as you go from inner to outer layer, the width of the trace increases because the inner layers don't typically have negative mutual coupling, right? So they anyway add a lot of resistance, so you can make them thinner. Okay, majority of the people, you can see they all have around 7, and they've all used like square multi-layer shunts. Okay, which obviously is comparable to this guy, octagon, but again there is going to be a small Q differential. And some people have used an octagon single layer. Okay, so as you can see in this particular case, because we are neglecting the eddy current losses, even a simple octagon is worse than a square multi-layer shunt, because the advantage you get from using multiple layers is much higher. Okay, and then if you just use a simple square, no multiple layers, you get somewhere around here. Okay, so this is just to show you, because now for the LNA project and the mixer project, there is no particular requirement for you to use the acidic inductors for your performance parameter. Okay, in other words, you are designing it assuming a Q of 10, assuming a parallel RLC. That makes things a lot easier, and mixer will also be the same. When you come to the VCO project, your inductor is pretty much going to be the most critical portion of your design. Okay, and for that you will not be allowed to use a simple RLC model. What you will have to do is, for the VCO project, you will have to choose you won't be given the value of the inductance just like the other projects. You will have to choose the value of inductance which is best for you, for your noise and your other parameters. Okay, then what you're going to do is you're going to go into acidic, model the inductor for that particular value, and you will see that, as we'll see in class, your phase noise has a very strong relationship to the Q of your inductor, and which again dominates the Q of the tank. Okay, so you will want to try to be somewhere here. You will want to try to maximize. By the way, of course, we have changed the acidic technology file after that, so you can imagine all of these things shifting up. Okay, so the performance of your VCO will directly depend on the Q of your inductor. That is what I want to, and that's the reason why I wanted to show you what other people have done, so that you can use, okay, this knowledge. Okay, now there was one more thing related to the project. Okay, now the project deadline was moved to Monday, and see, some of you, the reason why I decided to extend it was because some of you had problems earlier, and I thought since most of the learning is happening in the projects, you should have some more time because there are 4 holidays. So that is one thing. Some of you still went ahead and submitted it early. I'll definitely take that into account. Okay, because I know some of you put in extra work, and I'll take that into account. Okay, the other thing to know, which I wanted to touch upon, is for the IIP3. Okay, so remember that this is your IIP3. So if this is P out versus P in, this is your IIP3, right? Now what you can do, right, is you can try to bias the amplifier in such a situation where either one of these guys can be slightly non-linear. Okay, now that is not a desirable situation. I'll explain why. So you could have something like this, for example, right? Your third order could, because the main reason is, in class we assumed that the system is just purely third order. Okay, and the derivation of IIP3 and its use as the metric of choice for these kind of systems already assumes that your system has a very weak third order and your fifth, seventh order are all much weaker than that. Okay, now if you design the system such that it has strong nonlinearities, you can make it look as if the IIP3 is very good. However, where you will get hit is actually the dynamic range of the system. Okay, which means you really cannot use it in this region. Okay, so you can use it only in this region for lower level of powers. Now the LNA project did not have a specification for dynamic range. Okay, but in class we did cover that you want both curves to be linear. Okay, so people who are going to submit on Monday, I do not want to see any curves like this. Okay, I want you to have good first order and third order. Some of you have already submitted it. Again, I'll take that into account because some of you, if you can, you should go back and rework your design. If you cannot, I'll take that into solution because I did change the deadline at the last minute. Okay, I'll take that into account definitely. Okay, the reason is this kind of nonlinear behavior can happen when you operate at low powers. Okay, and that will artificially give you a feeling as if the system is very linear because we have used IIP3, but it's really not so. Okay. Okay. Let's move on to the lecture. So we'll continue with RX architectures. Okay. So last week we looked at direct conversion receivers. Okay, so today we'll look at heterodyne receivers. Okay, we'll quickly run through it because we've already looked at it in some detail before. Okay, and we'll move on to image reject. But first, let's see what this looks like. So we have this guy. You need the band select filter. You need the LNA. You need the image reject filter, and you have your mixer. Okay, you have some kind of variable gain. Okay, and you probably have something going on there. Okay, you have your baseband or your IF actually, not your baseband in this case, right? So biggest problem was the image, right? So which is what requires you to use the IR filter. Okay, so of course we don't, what the biggest problem this causes is if you choose a high IF you can get very good image rejection, right? Because the LO and the RF are very far away, which means the LO and the image are also very far away. So okay, and what does this translate to? Sensitivity. If you choose a low IF, sensitivity is bad, but you can do very good filtering at IF, which means your channel select filter. Okay, so which is selectivity. So there is an inherent trade-off between sensitivity and selectivity. Okay, and we saw this several classes ago. Okay, so now we will look at a couple of other issues, okay, with systems. So the first one is called the half IF problem. So let's take a simple receiver. So you have image reject filter, you have this guy, LO, RF, IF. So let's name these nodes A and this will be B. Okay. So let's plot let's say the signal at A looks like this. So you have the RF. Okay, so let's say you have the LO. Okay, so let's assume the image reject filter already takes care of the image. So in other words, let's call this as A. Okay. Now, if you consider a frequency here, let's call this omega 1. Okay, and omega 1 is omega RF plus omega LO over 2. So it is spaced halfway between the RF and the LO. Okay, which means the spacing from LO is omega IF by 2. Okay. Then what's going to happen is, we'll assume two more things which are very well possible. One is there is a second order distortion in your RF path. Okay, so we'll assume that there is a second order distortion in this RF path. Okay, and we'll see what happens if you have let's say the LO has a second harmonic. Okay, what is going to happen? So you're going to get an IF component at, so your second order distortion is going to produce a 2 omega 1 component, right? And okay, it's going to mix with the second harmonic in LO, right? This happens to be omega IF. Okay, is that clear to everyone? So in other words, if you plot this thing at B, spectrum at B, so you're going to have 0, and of course omega 1 is going to get translated to omega IF by 2. Going to be a desired signal, and you're going to get the second harmonic, which may not be so big, so something there. Okay, you're going to get that problem. Now what else can you have? You can also have a case where, let's say these two, let's say the second, you didn't have a second harmonic in LO. Okay, so naturally you won't get this component. Okay, you will still get this one though, right? Now what happens is, let's say if you have a second order, let's say you have a second order distortion in the IF, right? What will happen is, so let's say this is going to go through some kind of IF amplifier. Let's say this has a second order distortion. This is going to go and fall on IF, the second harmonic of that. Okay, so that is still going to happen. So your omega IF by 2 will go to omega IF. Okay, so what can you do to prevent these things? Obviously, reduce second order distortion in all systems, right? What else? Make sure your LO has very good 50% duty cycle. Okay, as close to 50% as possible. Because if you have 50%, exactly 50%, you don't have a second harmonic. Okay? Now you can, this is actually a single IF super heterodyne, so single IF heterodyne. You can actually have a dual IF or a triple IF also. So what you can do is, instead of having a single IF, you can have multiple IFs. So you can go down to a certain frequency, do a little bit of filtering, little bit of gain, and so on, and keep doing. So what that happens is you are basically distributing your filtering over multiple IFs. So what that means is your filtering for each IF is reduced, right? The filtering requirements for each IF is reduced. The only thing you have to remember is, so let's say it has IF1, IF2, you have to worry about you will have to do a second set of mixing to go from IF1 to IF2. You will have image reject problems there also. Okay, so because that mixer will have an LO and an IF input, IF1 input to go to IF2, and again you are going to have corresponding opposite side of LO, you will have omega LO plus omega LO2 plus omega IF2, you will probably have an image. Okay, so that is something you have to worry about. Okay, so that's as far as heterodyne systems. Okay, now let's look at image reject receivers. Okay, so the main motivation is you don't want to, image reject filters are, you can't implement them on chip, so they have to go off chip for good filtering. Again, you have to drive 50 ohms and so on. So that has motivated people to come up with architectures where you don't use a separate filter, you try to cancel the image separately. Okay. So the main idea is you can exploit the fact that one of them is at a lower frequency compared to LO, the other one is higher frequency, right? So you're going to try to perform some operation which is sensitive to this particular difference in frequency. Okay. So before that, we are going to look at what is the shift by 90 operation. Okay, because this block is going to be used for these IR receivers. Actually, let me go to the next page. So let's say you have a sinusoid, so shifted by 90 degrees, what you get is a cosine, right? Actually negative of the cosine. So okay, that is in the time domain. So look at the frequency domain, your sinusoid. Okay, so let's call this omega naught. Sinusoid looks like this. You want to convolve it with with this function. So this function is minus j signum of omega. Okay, and this gives you, of course, your cosine, minus cosine. So right, okay. So let's say you want to implement this in a circuit. So one very simple implementation is so let's say this is both capacitors and resistors are equal. Okay, if you look at VO2 has a phase shift of pi by 2 minus tan inverse omega RC. the other side has minus tan inverse omega RC. Okay. So what you will find is, so obviously the difference between these two guys is pi by 2. Okay, so you have an input signal, so output you are getting the same signal and a shifted by 90 signal, which is what you will want. We'll look at the architecture. This is what you want. Now the thing to note is the phase difference is pi by 2 across all frequencies. Okay, but the amplitude is equal only at omega equals 1 over RC. Okay. No. Pi by 2 minus tan inverse omega RC. You can go, go ahead and calculate, it's very simple. Okay. Okay. So let's look at this. So first we'll look at the Hartley architecture. By the way, at this point, right, you have 45 degrees on each side. Okay, you have 45 degree phase shift on each side. So this is what the architecture looks like. So you have sin omega LOT and you have cos omega LOT. Okay, so what you're going to do is you're going to take your RF input. On one side you're going to mix it with the sinusoid, sin omega LOT, go through the low pass filter, then you do a shift by 90 on that. Okay, on the other side you multiply with cos omega LOT, low pass filter, don't do a shift by 90 and go ahead and add the two outputs. Okay, so let's look at it mathematically, see what happens. Okay, okay, so okay, so we'll first assume low side injection. So remember, your earlier circuit had two outputs, each one has 45 degrees. Okay, so if you put it in here, you're going to have to put one here, one here. So effectively you want 90 degrees between these two paths. Okay, so these will produce the two outputs. So in the end, the other one is equivalent to doing 45 here, 45 here, and that will work too. That will be fine too. Effectively what you want, see, remember, this addition operation is going to be sensitive to the phase difference between the two. It's not, absolute phase does not matter. Okay. So let's call this actually. Okay. Okay. We'll name these four places A, B, C, and D. Okay. What do we have at A? So you have RF multiplied with the sine, okay, and the image multiplied with the sine. Okay. So let's assume your let's assume these are the two inputs. Okay, on your for your RF and image. Okay, so this is going to be the RF down converted to your IF by 2. So what we'll do is we'll rewrite this slightly differently. So we'll rewrite this as okay, we'll just rewrite this slightly differently because we have sign of A minus B is minus sign of B minus A, right? xb of t is going to be sum of the two cosines. So in one case you are multiplying with the sine, other case you are multiplying with the cosines. Okay. What do you have at C? So you are going to take A and shift it by 90 degrees. And we know that if you take a sinusoid, shifting by 90 degrees makes it a minus cosine, right? So this one becomes ARF by 2 cos of omega RF minus omega LOT. Okay. And then this one becomes minus AIM cos of omega LO minus omega IMT. Okay. And now if you compare these two, what do you see? The signal at D is just C plus B, right? The shifted 90 degrees plus the original B. The image portion cancels. One is positive, other is negative, right? Whereas the signal portion, cos of A is cos of minus A, right? So these two, signal portion is additive. Okay. So you have completely managed to cancel the image. And you can do the same thing graphically. So okay. So you can assume, look at this and do it. I'll just post it. It's very straightforward. Okay. So what you'll see is even if you do it graphically, again you'll have to, the 90 degrees you'll just do with the minus j signum of omega, and you'll find that you'll again get ARF, right, what you required, and the image cancels. Okay, you can start off with this guy and just do the operations just as you would normally. Okay, you can check the notes. I'll post it in the class. Post it on the website. Okay. So what are the major issues? So of course the major issues are you're trying to cancel something. Okay, you're relying on the fact that you have perfect 90 degrees and you're going to cancel plus and minus IM. Now what happens if you have amplitude mismatches between the two parts? Okay, and you could have phase mismatches between the two parts. Your sine and cosine may not be exactly 90 degrees, right? Your phase shifter may not be exactly 90 degrees. Okay, for example, we will look at this. If you have RC, right, on the RCCR, the network, the two resistors may not be exactly equal, or the two capacitors may not be equal. So these are all issues, standard issues, which you'll deal with. Okay. So the key issue is matching. Okay. So what we'll do is we'll assume that the two. Okay, and we'll assume that there is some amplitude error and phase shift error on one side. Okay, and you'll see that if you have amplitude errors in the, let's say, the gains of the blocks, you can include that here. So this is just, because it goes into the gain of the overall mixer. Okay, so what happens is you can write AFT as, so AFT stays the same. You can write AFT, it stays the same because it's just ALO sine omega RFT. What changes is XBFT, so that becomes okay, that is the first component, and again the image component. XCFT stays the same because XA has not changed. Okay. What is XDFT? So you're going to have, this is your desired IF component. Okay, you're going to get something from that, plus you are going to get some, I guess you can call it imperfect image cancellation, right? So you're going to have some error term. Okay, let's see what this is. Okay, plus so remember earlier the two things are equal, so you just got ALO ARF by 2 times cos omega LO minus omega RFT. Now you have one of the terms has an epsilon and a theta. Okay, similarly you can write the expression for the image, which will be ALO plus epsilon AIM by 2, and you'll have a minus term here. Ideally if epsilon and theta were 0, it would cancel completely, but now it won't. Okay, so now what you can do is, let's say we define an image to signal ratio. So you can define your image signal ratio as image power over signal power. Okay, and you're going to define what is called image rejection ratio. Okay, for this receiver. What is this? This is nothing but at IF over at RF. Okay, IF means the overall IF output after addition. So of course at the input it is just nothing but AIM squared over ARF squared, right? So here if you work it out, this is what you'll get. Okay, it's a lot of algebra, but this is what you'll get. You'll get something a squared minus okay okay, and this portion is at the output. Okay, where okay, A is nothing but ALO and B is ALO plus epsilon. Okay, if you make two more assumptions, we'll assume epsilon and theta are very small. If you do that, you can show that this IRR okay. Okay, so it end up being delta A by A whole square plus theta squared over 4. What kind of typical values will you get? You will see that your delta A by A is a few tenths of a dB. Okay, maybe 0.1 to 0.5 dB. Theta will be somewhere between 1 and 5 degrees. Okay, it depends how well you can do. So you can get somewhere around 40 dB of image rejection. Okay. Now let's go back to the previous implementation. So the RCR. So remember what I said, the goes through the mixer. So you have the low pass filter. One side. Sorry. Okay, you have a ground there. So R, C. And we're going to. So if you use an RCCR network, it is going to look like this, right? It's mod of? No, it's okay. It is mod of IRR. It's mod of IRR. No. Okay. IRR and magnitude should be low, but if you're looking at it in terms of positive dB numbers, so it is the image power over the signal power, right? Effectively, image power over signal power at the output over image power over signal power at the input. And at the output, ideally you want 0, so it's minus infinity. You're right. So it needs to be, but typically a lot of people use positive numbers. They'll say image ratios for 50 dB. So you understand that it's actually minus 50 dB is what they're talking about. So if you see typical IC, delta R by R can be pretty large and delta C by C can be pretty large. Okay, it can be like 10-20% easily if you don't do proper matching. So you can show that your IRR is approximately okay. So which means this can be as low as 20 dB or less. Okay. Okay. What else can you have? So you can have issues with, because the 90-degree block is going to add noise, and it can cause linearity problems. The RCCR won't have linearity problems because it's a passive circuit, but it will definitely have noise issues. Okay. Of course, there's going to be a power issue, because if it's resistive, CMOS circuits don't like to drive resistive loads. Okay, you need lots of power to drive resistive loads. So if you're going to drive an RCCR network, at least on one side you are driving a resistive load, resistive and capacitive, but at some frequencies it is resistive. Okay. Frequency deviation. So remember that the previous network matches only at omega equals 1 over RC. Okay. Obviously, if RC shifts, your omega naught will also shift, and your actual frequency of operation could differ from omega naught. So that could be a problem. So because of that, that motivates that motivated people to come up with a second kind of architecture, which is called the Weaver architecture. Okay. That is this guy. The half IF problem is independent, right, of what you're doing here, right? You could still have the half IF problem, definitely. So you should still try to minimize the second order distortion and so on. So this you're just trying to do it to kill the image, nothing else. So what you're going to do is, you're going to replace this shift by 90 with a second set of quadrature mixers. Okay. Oh. Okay, and of course the sign is slightly different here. I'm going to subtract. So let's call this A, B, C, D, and E. Okay, and of course we are also going to assume that omega 2 is much smaller than omega 1. Okay, second mixer is getting convolved with multiplying with sine omega 2t, just convolving with this, right? the other one is getting convolved with the cosine. Okay. So maybe let's do this graphically, be easier. So minus omega 1. So you have the image here, okay, and this is of course the image. This is your RF. At X-ray of omega look like this. Okay. You can look at the math, it's very straightforward. You just have to go back and look at the graphical method done for the first one. Okay. Convolved with this is just omega 2. And this gives you okay, on one side it's going to give you something like this, and similarly this is XC. If you go through the same thing for the other side, give you this plus this. Okay, so if you subtract the two, you'll get only the RF. Okay. Now remember that we talked about the problem of secondary image if you have a dual IF. So this is something like a dual IF, right? Because so if you have an image around omega 1, you're going to have a problem. Okay, so we'll see what happens there. So let's say this is omega RF and it's omega 1. So if you have an image at a frequency which is equal to okay, so let's look at a signal which is at 2 omega 2 minus omega RF plus 2 omega 1. So at the first IF, it's going to come down to omega RF minus omega 1. That's where the RF signal comes down to, right? Where does this guy come down to? Okay. And then at the second IF, so the desired signal comes down to omega 2, and this guy is also going to come down to the same frequency. Okay. So what can you do to prevent this? If you do this, okay, the final output will be at baseband because you're going first omega 1 and then omega 2, right? So then you don't have the secondary image problem. So you have the first IF, then you go immediately to baseband. Okay, so let's stop here.